Hello. In the previous lecture, we talked about laminar and turbulent boundary layers. We found that a turbulent boundary layer has much more friction than a laminar one. Here are the two equations for the skin friction coefficient of a flat plate. The laminar boundary layer is inversely proportional to the square of the Reynolds number, so to the power 0.5, and the turbulent boundary layer with the Reynolds number to the power 0.2. This picture here shows the skin friction coefficient of one side of a two-dimensional flat plate for both types of boundary layers. The blue line represents a fully laminar boundary layer, the red line a fully turbulent one, starting at the leading edge of the plate. Note that the x-axis is a log scale. The Reynolds number is based on the full length of the flat plate. At a certain Reynolds number, the skin friction of the flat plate goes up. This is the point where transition on the plate takes place. So, with increasing Reynolds number, a bigger part of the plate has a turbulence boundary layer, which is reflected in an increasing skin friction coefficient, until transition reaches the leading edge and the plate is turbulent over its full length. This slide shows the difference in the velocity profile between the laminar and the turbulent boundary layer. As you can see, the average velocity near the wall of the turbulent boundary layer is higher, which results in a higher skin friction. What we did not yet discuss is the transition process that transfers a laminar boundary layer into a turbulent one. If a fluid flow along a flat plate at zero angle of attack, at some point the laminar boundary layer will change from character. At this point, at some distance x from the flat plate leading edge, it will start to go turbulent. The Reynolds number based on this distance x and the free stream velocity is called the critical Reynolds number for a flat plate, just as there is one for the pipe flow in Osborne-Reynolds' measurements. An exact value for this critical Reynolds number for a flat plate at zero incidence is not so easy to establish. Measurements show a broad range of Reynolds numbers, since many variables play a role in the boundary layer development, such as surface roughness and the possible small disturbances in the free stream. In literature, often a lower boundary of 500,000 can be found. If we follow the boundary layer as it flows along the flat plate, then a number of stages can be identified. First, the boundary layer is laminar as it starts at the leading edge of the flat plate. At some distance from the leading edge, two-dimensional disturbance waves begin to form in the flow called Tolmin-Schlichting waves, or TS waves, after the two researchers that studied this behavior in detail. Further downstream, these oscillations grow in amplitude and develop into three-dimensional disturbances. And these vortices are unstable and break down as we go along the plate. They are followed by patches of turbulence in a surrounding of more or less laminar flow called turbulent spots. These spots grow both in streamwise and in spanwise direction. And when they have formed one front, the flow has become turbulent. This transition process can be sped up by surface roughness, adverse pressure gradient, and the like. Since it marks the beginning of higher boundary layer growth and increasing skin friction, you can imagine that it is worthwhile knowing where, for instance, on an airfoil transition takes place. There are several ways to establish the chord location of transition, and one of them is a method using fluorescent oil. The method is based on the fact that the turbulent boundary layer has a higher skin friction than the laminar counterpart. And this can be noticed in the way the oil is distributed over the airfoil. In this picture, an airfoil is placed vertically in a wind tunnel. The model is covered with fluorescent oil and it is illuminated by a UV lamp. The flow comes from the right and it starts laminar. The laminar skin friction decreases as we move along the model, and at some point, at about 35% of the chord from the leading edge, there is a black area with little or no oil, meaning that the local skin friction has increased dramatically. And this is where the flow is turbulent. The thick yellow part in upstream direction is the transition region. In the next slide, you can see how the transition location changes with increasing angle of attack. Now the flow comes from the left. The yellow lines indicate chord positions. First, we have an angle of 2 degrees with a transition location close to 40% of the chord. If we increase the angle to 6 degrees, we can see that transition moves forward to about 33% of the chord. The turbulent boundary layer drags the oil that was located between 33 and 40% downstream. As you may have noticed, transition is a complicated but intriguing process, and it is important with respect to the resulting drag of an object. It is sensitive to all kinds of disturbances, like adverse pressure gradients typically found on airfoils. Next time, we will investigate the pressure distribution around airfoils and how this influences the transition location.